I wrote here that the last two are tricky, but actually number 7 I don't think is terribly bad. Let's start with our vertical asymptotes again. We have a vertical asymptote at 0 and at 4. 1, 2, 3, 4. Yes, at 4. So that means x minus 0 and x minus 4 are in the denominator. And x minus 0 could just be shortened to x. So I have x times x minus 4 in the denominator, giving me my two vertical asymptotes. 2, 0 is my x-intercept, so that means x minus 2 has to be in the numerator. Now the only question is, do I have any other coefficients, like is there a coefficient in front of the x minus 2 or in front of the x that I should be concerned about? So I'm just going to check a few points. Now there aren't any specific points I can see that are easy to spot, so I am just picking a few values for x and seeing if the y value looks reasonable. So this is what I'm doing here. So the first one I picked is I used x equals 5. And I can see that y is somewhere between 0 and 1, a little over halfway. So when I put 5 into my equation, I end up with 5 minus 2 is 3, 5 times 5 minus 4, so that's 5 times 1, I get 3/5. 5 3/5 looks very reasonable. So then I picked 1. 1 looks like it's less than 1/2 for the y value when x is 1. So I put in 1, I get 1/3, and that looks correct. Then I put in -1. When I put in -1, I should get a negative number between 0 and -1. So I put in -1, I got -3/5, and that also looks reasonable. So I think my equation is correct. Now looking at the second one, this number 8 really is genuinely hard. Here's the problem. In number 8, I recognize it as a cubic polynomial with a positive leading coefficient, but I only know one of the zeros, and I don't have an equation to divide to find the other two, but I know that one of my zeros is -3, and the other two have to be imaginary because it only crosses the x-axis once. So I have x plus 3 as one of my factors, and some other quadratic factor that would have the two imaginary zeros as zeros. The other thing I know is that when x is 0, y is 6. So what I know that has to be true is that this number in the quadratic factor has to be 2, because if I put 0 in for x, I should get 6 for y. However, I don't know what the x squared factor and the x factor look like. They both could have a coefficient, which I'm going to call a and b. I don't know what those two are. So I need to have a couple of other points. And luckily, I can see a couple of other points on the graph. There are two other places where the y value equals 6, one at -2 and one at -1. So I'm going to substitute -2 into the function, into this, okay, for x, and it has to equal 6. So if I put -2 plus 3, a times -2 squared plus b times -2 plus 2, all of that has to equal 6. So that turns out to be 1 times 4a minus 2b plus 2 equals 6. Simplifying that, I end up getting 4a minus 2b equals 4. Then I'm going to put -1 into the function, realizing that also has to equal 6. Let me scroll up a bit here. Okay, so if I put -1 into the function that I have up here, this one right here, I end up with -1 plus 3, a times, that should actually be 1 squared, but it's still 1. Or it's -1 squared, which is 1. b times -1 plus 2. So 2 times a minus b plus 2 equals 6. If I simplify that, I end up with 2a minus 2b equals 2. So I have two equations with two unknowns. So I can figure out what a and b are by solving the system of equations. Fairly simple one to solve. And I end up with, subtracting the second equation from the first, 2a is equal to 2, or a is equal to 1. If I substitute 1 back into this equation, 2 times 1 minus 2 times b equals 2, so b has to equal 0. So I really have a very simple equation here. A is 1, b is 0, so there's no x term, and the constant I already know is 2. So here's the equation. It satisfies, it is a cubic equation. It has the correct y-intercept. We also know that these 2 points are correct, and it has the correct 0, the real 0. The two imaginary zeros we could solve for if we wanted to, but that's not the purpose of this question. So that is how you do that one. That's a pretty tricky one. If you're thinking, will you do that on the test? Oh no! Probably not, except as maybe a bonus question. That's kind of a lengthy problem, but it really does test your ability to think backwards through a problem.